Hello guys, welcome to another video tutorial of the course. So in this video, we will be talking about the operating principles of the switched reluctance motor. So let's start. First of all, let's review the advantages and disadvantages of this motor type. So we have several advantages for the SRM or SR motor. The first one is cost. As you can see here in this structure for the rotor core, we don't have any excitation on the rotor core. By excitation, we mean permanent magnets or winding, right? Or cage like induction motor. So in a surface mounted permanent magnet motor, we have alignment torque, and in an interior permanent magnet motor, we have both alignment torque and reluctance torque. But in this motor type, the total developed electric torque is only reluctance type, and in induction motor the torque is due to the interaction between the stator field and the rotor field, eddy current induced in the rotor cage of induction motor, and the operating principle is different. So this is one advantage for this motor type because the rotor structure is simple. It's not like induction motor. In induction motor we have to do aluminum casting, so the manufacturing process is more complicated. So this is actually one advantage of this motor type, right, in compared with induction motor or permanent magnet motors. So for a well-designed SR motor, this also could be an advantage from the efficiency point of view. In induction motor, we have ohmic losses in the rotor cage. So this kind of loss is not available in this motor type, right? So removing this loss type, we can improve the motor performance and increase the motor efficiency. The same situation is available in permanent magnet motors. For a, a specific combination, a slot pole combination, when the harmonic content, the content of harmonic flux density waveform in the rotor core of permanent magnet motor is high. Also, we can have high induced eddy currents and consequently high ohmic losses in permanent magnets. So from this point of view, if we design and optimize a switched reluctance motor, we can improve the efficiency. But also consider that in a permanent magnet motor, because the rotor core rotates at synchronous speed, the amount of iron losses is low. But in this motor type, we have iron losses in the rotor core because the frequency of variation of the flux density in the rotor core is high, and in the case of bad design, from this point of view, iron losses, we can lose efficiency. So this is important. The next one is easy construction, right? As you can see here, the stator winding is concentrated, and we have salient pole winding for the stator core. So the manufacturing of this winding is not as complex as distributed windings, right? When we have overlap in end windings, so the construction of this motor is easy, both for the stator core end winding and the rotor core. The rotor core is mechanically robust, and this option makes high-speed operation possible. Also consider that we don't have a high back EMF at high speeds for this motor type, and in the case of single pulse switching, we can reach high speeds in this motor type. Okay, in a surface mounted permanent magnet motor, if we want to increase the motor speed, we should use field weakening, right, to reduce the amount of back EMF to be able to reach high speeds. But this option is available in this structure, and also we have a good power and torque density in this motor type. So in this course, we will design the SR motor and we will compare with the benchmark induction motor. Because we have a good saliency ratio, by saliency ratio, I mean the ratio of aligned inductance per unaligned inductance. If we optimize the design and increase the saliency ratio, we can have a good amount of reluctance torque, right? And actually the torque density is considerable in compared with the induction motor. The next advantage is the converter reliability. So what is this option? Here in this figure, you can see the three-phase bridge inverter, right, with diode rectifier for induction motor, speed control. We have a three-phase power supply here, diode rectifier, and we have a three-phase bridge inverter. And induction motor is here, three-phase induction motor. So in this circuit, as you know, we have risk of short circuit, right? Short circuit fault when, for example, Q1 and Q4 are on at the same time. We have short circuit fault here. So we should consider, right, safety guidelines to impede the short circuit fault in this circuit. But in a switched reluctance motor, this is, for example, the asymmetric converter for SRM. This is for one phase. For other phases, we can have this branch in parallel, right? So this is for one phase. And as you can see here, we don't have the risk of short circuit fault in this circuit, right? When we turn on T1 and T2, we have the direction of the current, right, in this direction. And when we turn off T1 and T2, this is the direction of the current. And the value of inductance of each phase in a switched reluctance motor is high, and we don't have the risk of short circuit fault here. So this is also an important advantage for this motor type. But we have two disadvantages. In this motor type, the torque ripple and noise is high because to have a continuous rotation, we have to turn on and turn off coils related to each pole sequentially, and we have a commutation, right? So torque ripple due to commutation is high. And to reduce this torque ripple, we have two options. We can optimize the rotor core geometry or use complex control methods to reduce the torque ripple. So the control of this motor is complex, and to have a smooth torque, we should implement a complex control method. In this course, we don't discuss complex control methods for this motor type to reduce the torque ripple. This is an introductory course, and in this course, we will learn how to size the motor, how to derive the important performance curves, right? So this is actually an advanced topic. So here you can see an example. We have a 6x4 SRM. The number of stator poles is equal to 6, and the number of rotor poles is equal to 4. In this structure, the number of phases is equal to 3, right? As you know, the number of winding coils is equal to the number of stator poles, and coils with the same value of inductance for a specific rotor position belong to the same phase. So in this case, as you can see here, these two coils belong to the phase A because the value of inductance for these two coils are the same. So here in this example, if we excite the phase A, the value of reluctance torque will be equal to 0. So we cannot generate electric torque. But if we excite the phase B, as you can see here, the rotor will be rotated in clockwise direction, and we have this case. So the value of reluctance torque will be negative, right? If we consider the counterclockwise direction, right? The positive direction. So the value of reluctance torque will be negative. And if we excite the phase C, we have this case, and the value of reluctance torque is positive. So how we can have a continuous rotation? We should have a continuous switching, right? So if we excite the phase B, right, we will have this case. And in this case, if we excite the phase C, we will have this case. And then when we excite the phase A, we have this case. So we have a clockwise rotation, right? So this is the direction of switching BCA, right? BCA, this is counterclockwise, but the direction of the rotation is clockwise. And if we have this switching strategy, if we excite the phase C and then excite the phase B and A, actually clockwise switching, we will have a counterclockwise rotation. So in this example, the direction of switching is in opposite direction of the rotation of the rotor. So this is a 6x4 three-phase SRM, and as you can see here, if we want to have a continuous rotation, we should have a continuous switching of each phases. For a clockwise rotation, we should have a counterclockwise switching, and for counterclockwise rotation, we should have a clockwise switching. You know, here in this case, the value of reluctance torque doesn't depend on the direction of the current, right? So the direction of the current is not important. So this was an example. And here is the question. Do we have this situation for other combinations or not? So you can search in the reference books of this course to answer this question. So this is a practice to search and answer this question. Do we have this situation for other combinations or not? Can you find a combination that the direction of the switching is the same as the direction of the rotation of the rotor? Anyway, so we will use this logic later when we want to do a steady state simulations or dynamic simulations of the motor. Now let's discuss the ideal phase currents. Is the switched reluctance motor a DC motor or an AC motor? So for a continuous rotation, we should turn on and turn off phases of the motor sequentially. So each excitation is one stroke, right? Each excitation is one stroke. And what is the electric period? By electric period, I mean the electric period of the phase current, right? We have periodic phase current. And what is the electric period of the phase current for the SR motor? We should find the number of strokes. Here you can see in this figure, we have excitation for the phase A, then we have the excitation for the phase B, and then we have excitation for the phase C. The terminal current is summation of the IA plus IB plus IC. This is a DC current, and also we have a DC voltage. This is a DC motor. So this is the ideal case, and in real case, we don't have this situation. But in this ideal case, we can find the electric period. One electric period is defined when a rotor pole moves from an aligned position to the next similar position, right? So this is our convention. This is one electric period. We have this unaligned position. This is the phase A, and the phase A is in its completely unaligned position. We have rotation, and finally we have the same position. So we have actually one electric period for rotation of the rotor. The rotation is equal to the one rotor pole pitch. So what is the number of total strokes in one rotation? If you look at the phase A, for one rotation, for one complete rotation, the number of poles, right, will be in front of each stator pole. All poles of the rotor core, right, will be in front of the stator, one stator pole, that is equal to NR, and we have M phases. M is the number of phases. So number of strokes in one phase in one rotation is equal to NR. Total number of strokes in one rotation is M times NR. So what is the frequency of the phase current? The frequency of the phase current is NR times RPS, revolutions per second, right? So Fs, the frequency of the phase current, right? This is the current of the phase A, B, and C, they have the same electric period. The frequency of current is NR times RPS. RPS is RPM divided by 60 revolutions per minute. And the electric period is the reverse of the frequency, that is 60 divided by NR times RPM. So this is one electric period of the phase current. This is an important equation, right? So the electric period of the phase current depends on the rotor speed and number of rotor poles. When we increase NR, the frequency of phase current increases. And when we increase actually the speed, the frequency of phase current increases. So in cases when we want to design high speed switched reluctance motors, we cannot increase the number of rotor poles because we will have a high frequency current, the frequency of variation of flux density waveforms at different locations of the motor is high. We will have high iron losses. So for high speed applications, we should limit the number of rotor poles. So yes, you can remember this important equation. Later, we will use this equation multiple times. So in one electric period, we have m strokes. Total number of strokes in one rotation is m times nr. Number of strokes in one phase is equal to nr, and this is the frequency of the phase current. So, okay, in this video, just I wanted to explain the operating principle, right? A quick review, and from the next video, we will start the analytic design of the motor. So you can review this video and let me know if you have any questions below this video. So thanks for watching.